That part. Okay. Okay, so the first steps that we do with all these limit problems is either one of two things. Whenever you see a number, just plug in that integer. Don't do decimals, right? If you see infinity, don't plug in 100 or -100. Go ahead and compare degrees. Right? So those are always the first two steps. If you jump to decimals, if you jump to 100, it's going to throw you off. So that's only for certain situations. Okay, so let's look at A here. Okay, so we have to decide which piecewise function is going to be most appropriate. We want to approach -4 from the left. So which piecewise function is on the left side of -4? First, second, or third? First one, yeah. So we want, these are x values to the left of -4, less than -4. So it's going to be the first piecewise. Okay, what's our first step? Plug in what? Just -4, right? Okay. So we get 9 minus 16. In the denominator, we get 0. So this is very telling, right? What does that tell us is happening there? There's a vertical asymptote. Normally, we would say the limit doesn't exist, but it's a one-sided limit, which means that we're asking about the approach towards -4 from the left side of -4. Now there's only two options, right? It's either going to go up or it's going to go down. How do we choose between these two? Because we can't see the graph. So now we can use what?
-3, -4.1.
Yeah, we use decimal. So we want to choose a value that is really close, relatively close to -4 from the left side of -4. And then whether we get a positive or negative is going to determine for us which direction the arrow is headed, either going up or going down. Okay, so now we're going to test the decimal value. So decimal value gets inserted in for x. All we care about is the positive or negative value. So we don't have to worry about what this decimal ends up being. We just care about the positive and negative. So if I put -4.1 in for x, 9 minus like 16 point something, right? 9 minus 16-ish, that's going to be still a negative. And then -4.1 squared, that's going to be like 16 point something. Minus 16 is going to be positive. Negative or positive is negative. So we know the graph is going to look like this. We're approaching an asymptote. We're only asking about how the graph is looking from the left side of the asymptote, and the decimal is going to help us determine which direction it's headed. Okay. Part B. No, you don't. I just want to just show you that if there was not a one-sided limit, then you would say limit doesn't exist. Right? But if it's one-sided limit, we have to just look at the behavior. We can't say it doesn't exist because it's only asking now about the movement towards the asymptote from just the left side.
So like in the case that it asks limit x approaches -4 without the like.
Yeah, we can just stop. We can just stop and say DNE. Okay, part B. Approaching negative infinity. Okay. Which piecewise function are we choosing if we're headed towards negative infinity? Still the first one, right? Yeah. And how do we deal with infinities? Compare degrees. Yeah. We don't plug anything in, right? We go directly to compare degrees. All right, what do you notice? Same. So what's our limit? Yeah, it's just like finding horizontal asymptote, right? We take the ratio of the coefficients. There's a -1 in front of x squared. There's a 1 in front of x squared, -1 over 1. It's negative. Part C, approaching -4 from the right side of -4. Possible, okay. Because we want to, the greater than is telling us this graph is living to the right of -4. Right, what do we do? What's our first step? Plug in -4, right? No decimal, just the integer. Okay, what do we get? We got a real number, so there's nothing more to do, right? There's no hole, there's no asymptote, the graph is continuous, the limit is just direct substitution. Okay, part D, limit as x approaches -4. How do we do this one? We're tempted with 2 minus x because we do see that x equals -4, but what's the issue? Because this is just a what? Just a point, right? We know a point has no say on what the limit is. So in order for the true limit to exist, if the graph is split on either side of -4, we have to look at it from the left and from the right side. We have to look at the arrows from both sides. And do we have indication how the graph is moving from both sides of -4? From the left, it's going down. From the right, it's going to +8. Are they approaching the same y value? They're not. Therefore, the limit doesn't exist, right? If you were looking at the graph would not be showing the arrows pointing to the same y value. We'll say DNE. You don't have to write this, but the reason why is DNE is because the approach from the left of -4 is not in agreement with the limit as x approaches -4 from the right side of -4. Okay, part E. Okay, limit as x approaches +infinity. Which one do we look for this one? Last one, okay. And what's the first thing we do if we see approaching infinity? Compare degrees, right? What do you notice? And the numerator is the one that's greater, right? So we know this fraction is getting larger and larger. It's either go in two directions, right? It's either going to go up towards infinity or it's going to go down towards infinity. But we do know that it is growing in one of those two directions. So now that we know that it's one of these two options, now we can decide between those two by doing what? Testing 100. Yeah. All right, so 100 in for x. Numerator, we get negative. The reason why is because the negative is outside the x. So we get 100 squared first, and then the negative tags along. The negative is not getting squared, just the x is. So negative over a positive. Because we're looking for end behavior, we know that this graph is headed towards either positive or negative infinity. And if we go out to 100, we can have an idea where the graph is headed. If it's positive, we know it's probably going up. If it's negative, it's going to go down. So negative or positive is negative. Yeah, so again, the most common mistake that students make is going to the decimals too soon or going to 100 too soon. Doing these as the first steps, right? Make sure that your first steps is always direct substitution for real numbers and comparing degrees for infinity. That way you're not making assumptions before you actually do the first steps. Okay, number 2, sorry, 1b, says step through continuity conditions for number 1, then state the reason for discontinuity, identify top discontinuity at x equals -4. So we're going to step through continuity conditions for each starting with the point. So first condition, the point exists. Where do we find our point? Middle one. Okay. Second condition, does the limit exist? We have to rely on 2 limit statements. But we already gathered that from part B and D, right? So, and we already know that they're not in agreement. So we can just say limit okay. Therefore, what can we conclude? Because the one side limits are not the same. Yeah, the limit doesn't exist. Okay. Make sure you're writing out your full statements, that you're including the name of the function with each limit notation that you're writing. And what type of discontinuity can we call this? Second condition fails. Yeah, non-removable. Okay. Number 2, find the horizontal asymptotes. We know that this is a strange looking graph potentially because maybe the graph looks something like this. You don't have to have a graph calculator, but I just want to show you that if there's a radical below and none above, maybe our graph could look something like this, where there could be a split asymptote on either side of infinity. But we know we're going to look at both infinities. So we know horizontal asymptote is always approaching infinity. Well, we can find asymptotes by looking at end behavior, and end behavior is limit as x approaches infinity. So let's just go through our rules and see what we discover. So what do we do if we see infinity? Compare degrees. What's degree of the numerator? 1. What's degree of the denominator? It looks like 2, but it's really a 1 because the square root is going to undo that down to a degree 1. So what happens if degrees are the same?
You just divide
Divide the coefficients. What's the coefficient of the top? And the bottom is?
Would that be 2?
Yeah, that's right. The 4 is getting impacted by the square root. So root 4 is 2. So therefore, negative 1/2. So that means as we head to the right of the graph, it's doing this. It's flattening out at negative 1/2. But we know that there's something strange about the radicals, so we also need to look at what's happening if we're moving to the left of the moving left off the grid. So if we're pushing infinity or negative infinity, it's always comparing degrees, right? So our degrees is still going to tell us negative 1/2. But something a little bit strange about negative infinity is that let's just see what happens with the sign of this expression if we were to plug in, like, let's say negative 100, just so we can convince ourselves. Does it really go to negative 1/2? So what happens if I were to plug in like negative 100? What happens to the numerator? Positive. And the denominator? Still positive, right? Because that x squared is forcing everything to be positive. So we got a positive over a positive. So this is going to change. And now it's going to be 1/2. So that means as we approach right, it's going to negative 1/2. If we approach left, it's going to a positive 1/2. The graph looks something like this. There's different asymptotes on either side of infinity. Yeah. Yeah, whenever you see this scenario where you have the degrees are the same, but one side has a radical, it's always going to do this. No, you don't have to. I did this to convince you that there's going to be 2. So what would our answer be? Because it's asking for horizontal asymptotes. Good. You got to say y equals. These are the limits, but asymptotes are equations of lines. So y equals 1/2.
Why would the second limit just switch to the negative 1/2 to 1?
So if I were to test a number that is headed towards negative infinity, I would always get a positive number,
Oh,
right?
yeah.
But then if I were to plug in the positive 100, well, in this case, I'm just comparing degrees, and then a positive 100 is not going to change the signs here, so it's going to stay here, I think. Yeah. But the big picture is there's always 2 asymptotes if the degrees are the same and one side has the radical. If it is a strange scenario like this. If it's not, if it was like find the horizontal asymptote, so y equals to x cubed plus 4 over 2x cubed plus 1, it's just going to be 1/2 because it's going to be the same asymptote on either side. It's just, this is a very special, unique scenario. And it's covered, this is technically in our scope of what we need to learn. So, but most graphs don't look like this. But you don't have to show all this work on the test. You can just, that you're comparing degrees, there's 2 of them, and they're always going to be the same ratio, just different signs. Okay, intermediate value theorem. This is number 3. Okay, show whether IVT applies. Again, to remind us what IVT is, we first have to convince ourselves the function is continuous on the closed interval. Make sure that if there are any asymptotes or holes, that neither are interfering with our interval. And then second, we're trying to guarantee this y value. We're trying to guarantee, is this y value going to hit somewhere between x value when x is 4 and x equals 8? So what we need to do is we need to plug 4 and 8 into the function, and we're looking for y values that are above 2 and below 2, because we want to either start below 2 or above 2 so that we can guarantee that we can cross through a y value of 2. So continuity is our first condition. Is there any discontinuities in my function? And where do we find discontinuities in a function? Where's the issue here? Do you see any holes or asymptotes? There's a vertical asymptote where. Sorry, how'd you find that? Yeah, you always look denominator, right? Denominator is going to be where your discontinuities are. So it doesn't matter whether it's a hole or an asymptote. We just know that there's a discontinuity. There's a break in the graph at x equals 3. Is that the only break in the graph? I mean, remember, horizontal asymptote is not a discontinuity. It's just an end behavior. It's just holes or vertical asymptotes. That's the only issue. Do you see any other hole or asymptote in the denominator? This is the only discontinuity, right? That's what convinced us that there's no other hiding discontinuities in this problem. So there is a discontinuity. Doesn't mean that we stop the problem. We have to look at what? Does it interfere with the interval? Is this an issue? No, right? If the asymptote was between the interval, then that's an issue. Then we can stop the problem and say function is not continuous on the closed interval. We stop, and IVT doesn't apply. But here, there is a discontinuity. That's the only discontinuity. It's outside the interval. There is no other discontinuity. This interval is safe. Our function is continuous on the closed interval. That's the first condition. So we can move on with our problem. Are we good with that? So now, next, we need to find where these y values are. We're hoping that we get a y value below 2 and a y value above 2, because we're trying to guarantee that there's a y value 2. We're just using very limited data here. We don't have the graph in front of us. We're not going to put order pairs. We're just depending our reasoning solely on the endpoints and the fact that the graph is continuous, that there are no breaks in the graph. Okay, so f of 4. So if I plug 4 in for x, what do we get? Yep. If I plug 8 into the function, and we know 8 over 5 is like less than 2, right? We know 10 over 5 is 2, 8 over 5 is like 1 point something. So we're trying to guarantee a y value of 2. Can I guarantee that there's going to be a y value of 2, that the graph is going to cross y value 2 somewhere between? Yes. Okay. So maybe we don't, maybe we don't know what the graph looks like, but we do know that we're going to start off at 4, 4. And we're going to end up at 8, 2. Or 8, 1.9. And we're trying to see, oops, sorry, 1.9 is here. Oh, 1.8. And here's our target. Our target is we want to know, is the graph going to cross this y equals 2 somewhere between? Okay. And the graph has no choice but to cross y value of 2 because it's starting at 4 and it's ending at 1.9, and the graph is continuous. It's got to hit 2 somewhere. Right? We don't know where yet, but we do know it's got to cross 2. Makes sense? Some of the mistakes I see students make is they look at the 2 and they say, well, 2 is not between 4 and 8, so it doesn't work. Why is that not a good comparison? Yeah, you're right. You're comparing y value with x values, and we don't have the data yet, right? We need to actually find the y values before we can see if this is between the 2 endpoints. So we can say by IVT, we've already established continuity, so I'm looking for the statement on as your Parger reasoning. Since we have an endpoint that is clearly below my target, since f of 8 is equal to 8/5, and 8/5 is lower than 2, and 2 is lower than my other endpoints target y value, there must be a c value. Remember, c is just a it's just a x value solution that we're looking for.
What if, when you plug in 8, it's higher than 2?
Then we stop the problem. We say IVT doesn't apply because we don't have this scenario doesn't, we don't, f of 2 is not between 4 and 3, right? So now we have that guarantee. We know the graph is going to touch a y value of 2 at least once, somewhere between 4 and 8, because it's got to cross through. And now the next step is, where is that x value? So how can we find the location of this ordered pair? Do we have enough information to do that? Okay, we have the y value. We have the function. Yeah, just plug in, right? So plug 2 into what? Into the y, right? Remember, that's the y value.
Hey, did you print out the thing for me?
No, I didn't. Not yet.
Oh, okay.
Good job, though.
You did good, didn't you? Oh, sorry. Okay, how come? Will you have that later, you think? I
Huh?
can get it from you later? Later you do it?
Maybe. I don't know.
Maybe. Yeah, don't worry about it.
Yeah. Maybe like 5th period. We'll see. All right.
Thanks, man.
Yeah.
We'll catch up later.
Okay. So 2 in for y, right? And then we can solve for x. Cross multiply, and we can solve for x. X equals 6, so c is equal to 6. So our order pair is 6, 2. 2 is between 8/5 and 4. And then our c value, our x value location is also clearly between 4 and 8. Right? So all those things have to line up, right? Our x value needs to be between our interval, and then our y value guarantee has to be between the y values of endpoints, right? So we're comparing x with x and y with y. The only thing to watch out for is if I get c equals 6, let's say it ends up being c equals 6 and c is equal to 9. Can I keep both of these x value locations? let's say the graph crosses the crosses the y value of 2 at 6 and at 9. Can I keep both of these locations? What do you guys think? The answer is no, we can't keep that 9. Why is that? Yeah, it's not between 4 and 8. We only care about what's between 4 and 8. If something is outside the 4 and 8, it's not part of our problem. So, yeah, I mean, it didn't show up, but I'm saying sometimes there's two potential solutions, and we always have to pay attention to what our problem is, where the problem is for us, right? If it's outside of our domain, then it's not going to, even though it may hit that point, if it's not part of the problem, our problem, we have to move it out. Okay, let's try one last one here. This is just looking at the graph and finding the limits. So if you guys can try that, number 4, and we can compare our answers on the back.
Can I show you that in class?
Yeah, show it to me.
Okay.
I'll see you.
Thank you.
Oh, right here. So that means as I'm following the graph to the right, is the graph flattening out? So we do see that this y value is flattening out, that there's an indication of a horizontal asymptote at y. Oh, sorry, over here. As we follow the left arrow, as it exits from view, it is flattening out at y equals 3. It's like a horizontal asymptote here. Yep, that's right. That's right. Well, yeah, if it's just one side, you just look at the arrow from the left side, that's it. Yeah. If you see a limit with no plus or minus, that means it has to be arrows on both sides had to be in agreement. So if we do limit, we always start off by picking a point to the right of 4. So to the right of 4 is this one, right? And now I follow the graph towards 4 and I ask, where is that arrow headed? Yeah, the negative. Right. What was your question? On this side? Because the arrow's not headed there. Because that's not part of that's, this graph will get closer towards this point, but there's a break. There's no way this arrow will ever get close to that point. Now, if it was limits as x approaches -4 from the left side of 4, then I pick a point on the left side of 4 and follow that arrow, and that is taking me to this.
I get it, because that was the first line on the coming in from the right hand.
Right, yeah. So this tells you want to start at a point to the right or to the left, and then move towards that target. Okay, so we'll continue review in class. We'll continue picking out problems from the review packet. We have class period today, class period tomorrow, and then Wednesday morning help session.
Are we just back in turn?
Not turned in. I'm not taking it for grade, but I think just by us doing it now and Monday, Tuesday, and Wednesday, we'll probably finish everything. I'm not taking up for a grade. Right, homework is just your AP practice.
Or like
Which-
for today, it's just practice.
Yeah, there's no homework after today. Yeah, there's no homework tonight. Tonight, tomorrow, you're just studying for your test. Okay, so today in class, we'll probably finish page 6. And then we'll try to do page 13, 14.
All right.
And the keys are all attached. All right, see you in class.